Yeah, thank you very much. Hi, everyone. My name is Clemence Fontanive. I'm a postdoc fellow at the University of Montreal. And today I'm going to try to give you a bit of an overview of what we've learned so far from all the surveys that we've been conducting with direct imaging, and mostly by looking at results at the population level. So what we've been learning about the demographics and formation of these objects, but also all the stuff that we still don't really understand. Ooh, what happened? Does this work? Yeah, okay, cool. So we've been hearing a lot this week that we have made tremendous progress over the last decade or so in direct imaging. I stole these beautiful diagrams from Brendan Bowler. But first I wanted to take a step back and sort of reflect on where all these new detections that we finally have actually came from. So when we're designing a direct imaging program, the first thing we need to ask ourselves is, what is our primary goal? Because this is actually going to drive the way that we decide to do things quite a lot. So we're going to be talking at all about characterizing things that we know. I'm really talking here about designing a program where we're just going to observe stars in the hope to find new companions. So you can have two main primary goals here. The first one is going to be to do things in an unbiased way so that we can measure the frequency of planets, so occurrence rates and demographics. And the second goal you might want to go for is to just increase the number of planets that we know and have more detections. In an ideal world, we'll be able to do both of these things with the same surveys. We know from direct imaging that this is not the case. So we'll end up with two main categories of programs. The first one, if we want to do occurrence rates, we have to do some blind surveys where we do things in an unbiased way so that we can do proper statistics. And then if we want to boost our detection rates and just increase our sample sizes, we're going to have to go through more informed or targeted searches. And then there's a few other choices that we have to make when we design a program. So the first one is that we know that brown dwarfs and giant planets, unlike stars, they don't have a main sequence. So they don't fuse hydrogen, they don't have this internal source of energy sustaining them. And that leads to a luminosity mass age degeneracy. So what it means is that these substellar objects that we have here, they spend their entire lives cooling down. So the first choice that we have to make is this compromise between age and brightness, because if we observe things when they're old, they will have really faded, and we're going to have a lower chance of seeing them. So typically, most direct imaging programs so far have been focusing on really young things because that gives us a better chance of actually detecting low mass things. Then if we go in for young things, we also have to make the choice of which young cluster do we look at. And again, that's going to lead to a compromise or a choice we have to make between distance and youth. So we saw a similar plot to this one earlier in the week. So it's showing some of the nearby young star forming regions and moving group and clusters, where we have the distance on the y-axis and the cluster age on the x-axis. And you can see that ideally we'd want to be down here. We'd want to look at things that are super close to us so that we have the best inner working angle and can look at close-in planets that are also still really young and really bright and easy to detect. But it happens that the very youngest stuff are actually a bit more distant and the closest stuff are a bit older. So maybe your choice is going to be driven by your science case, but either way, you're going to have to make some sort of compromise between your access to lower masses and your access to closer orbital separations. And then finally, a third choice that we have to make is the choice of wavelength, which again is going to come at the cost of resolution. So again, we saw this plot earlier in the week. So this is showing how the contrast of planets or brown dwarfs of different temperatures vary when they're around a sun-like star. And because these brown dwarfs or giant planets mostly shine in the near-infrared or possibly even the mid-infrared if they're really cold, you get a better contrast by moving to redder wavelengths, but then you also lose in resolution. So again, you kind of have to make a choice between your resolution and your contrast. Okay, so all this to say that we've been doing many, many surveys. They finally led us to a decent sample of objects with direct imaging. And all this detection came from different surveys that did things differently with all these different options that I just explained. But generally, most of these actually came from what we call these blind surveys, so things that we can actually do statistics with, mostly on current 8-meter class telescopes looking in the near infrared. and with a bias towards very young ages, which are the stars that have been mostly targeted so far. Okay, so since most of the current discoveries are have been made with these blind surveys, let's start with these and what we've actually learned in terms of demographics. So there's been many different programs looking to constrain occurrence rates, which is the main astrophysical parameter that we can constrain with our blind surveys. This is a little summary of some of the many surveys that have been conducted over the last decade or two. And before I get into actually looking at these numbers, there's a couple of things I want to highlight, which is that you have to be really, really careful when you try to compare these numbers. And that's for multiple different reasons. The first one is that occurrence rate only means something over a specific range of masses and separation. If I say that stars have a frequency f of planets around them, I have to define what sort of planets I'm talking about. So I have to say a fraction f of stars have a planet between separations of x and y and masses of z and z2. And all of these surveys have actually constrained things on different boxes in this parameter space. So we have to be a bit careful, and we can't directly compare these two numbers if they're not constraining the same sort of planets. Then the second thing is that there can be different ways of actually defining what's on the y-axis here. So here everything is plotted in terms of planet occurrence rate, but that can mean two things. We can define this as the average number of planets per star, so saying I have X planets in my sample of N stars, but we can also define this as the number of planetary system per star. So there's N planets, N stars in my sample that have at least one planet or brown dwarf in the range I'm looking at. So it's basically a deal of whether you count HI 799 as one planetary system out of your N stars or as 4 planets out of your N stars. And given that we don't have that many planets, that changes that number quite a lot. So again, something to be careful about, like make sure if you're trying to compare these numbers that you check how things have been done. And finally, the statistical analysis that have led to any of these numbers are all done in their own way. We have to make so many assumptions. There's many ways to do things. There's almost as many ways to do these statistics as there have been published surveys. We try to do things in a way that is as unbiased as possible. We're still humans. We still bias ourselves. It's really hard to account and correct for these biases. And we somewhat all do it in different ways. So in particular, a lot of these surveys have the same planets included in them. And sometimes it's because you define your initial sample of 500 stars, you end up only observing 200 of them. But you know that there was a star in your sample that another team found a planet around. So you want to have that star in your sample so that you have a detection in your final statistics. So how do you account for the fact that you chose to observe that star as opposed to another one? So I do try to correct for this, but there are multiple ways to do this. So just wanted to highlight that we should be careful when comparing these numbers. Luckily, we still all agree, roughly, on the fact that wide orbit giant planets are not very common. And we've been gradually improving these constraints down to a planet occurrence rate, depending on how you define this, of a few to maybe 10% for the part of the parameter space that we're currently looking at with direct imaging. So I also want to take this chance to highlight that there's many null detections in what I've been showing you. So all the down arrows are null detections. So surveys that have no planets discovered in them. I know non-detection results are not the sexiest thing, but they're still really valuable. So please publish your null detections. They're really important science results. And in fact, it was worth persevering because these first generation of surveys that we conducted all had null detections, but eventually we had some. And I'm not going to go into the details of how any survey actually did things, but I did want to highlight a few of our favorite systems that actually came from some of these blind surveys. So HI 799 was discovered as part of the International Deep Planet Search. We have GJ504b, which was found as part of the SEED survey. You'll recognize 51AB, which was discovered as part of GPIs. And finally, we have the embedded protoplanet PDS70b, which now has a sibling that was discovered as part of the SHINE survey with the VLT. And with this is what the sort of masses and separations that we've been reaching with this last generation of surveys. So we have the results from the Gemini GPIs program on the left, and then the VLT Shine survey on the right. So you can see that we're mostly sensitive. So this is kind of showing you the masses and separations of planets that we could have detected in this program for a certain fraction of stars in the survey. And our best completeness, which you can see up here or up there, is roughly for high mass giant planets or brown dwarfs on orbital separations of a few tens to maybe 100 astronomical units. And then for planets outside of that range, we could only detect them around a fraction of the sample. And then typically what we do to constrain occurrence rates is that we take into account this completeness map so that we know what we should have been able to detect if it was there, but we can also correct for what we may have missed. And then we take into account the position in this parameter space of all the detections that we have, so that you can see with all the colored dots over here. And from this, we try to infer an occurrence rate that is the most compatible with our observations, based on some underlying population distribution. And the idea, the ultimate goal behind this is to then try to track this back to formation theories to try to understand where these detections that we have came from, like how they formed. So for the part of the parameter space that we're currently probing with direct imaging, we think that there's possibly up to 3 dominant formation mechanisms. So the first one at the very bottom here, which is probably forming the lowest mass giant planets on the tightest separation, is core accretion. So this is when you have an accumulation of small pebbles and planetesimals. At the very top up there, for the really most massive and widest companions, we think that they probably form through the direct collapse of a molecular cloud. So this is just like star formations. So companions that would form this way would be like a miniature binary companion forming like a star. But then we also potentially have like this in-between mechanism which is gravitational disk instability. So the idea here is that you have your disk around the star, and if it becomes gravitationally unstable, it can fragment onto itself and form, again, a giant planet, a brown dwarf, possibly a low mass star. So there is definitely an overlap that is expected between the outcome of all of these. For any single object, it's going to be almost impossible to tell for sure how it formed. But by looking at populations and demographics, we can try to see if there's some tendencies on the overall populations that we see that could be explained by some or combination of some of these. 3 is actually a bit too much for us, so we tend to reduce these 3 possible mechanisms down to only 2. But again, we don't like to do things in a homogeneous way, so there's been 2 ways to do this. The first one is to combine these bottom 2 mechanisms in a disk-based formation process, as opposed to a binary star formation channel. But we can also think about this as this being a bottom-up process, and these 2 combining into a top-down mechanism that is more similar in terms of physics. Unfortunately, once again, direct imaging is mostly sensitive to what we expect from this middle bit down here. So depending on how you decide to do things, it can be a bit tricky to compare results from different surveys that may have done things differently in the interpretation of results. So if we take that example of the bottom up compared to the top down model, here we have the detection limits of the NACO large programs. So the curves that you see up here tell you the sort of mostly brown dwarfs that could have been detected in this survey. And overplotted in the colored dots are the expected outcome of synthetic populations for gravitational instability at the top, and then core accretion here at the bottom. And the main thing that comes out of this, so there are a couple of detections here. They look similar to the blue dots, so it's a bit confusing, but they're over here, here, and there. It looks like these have to come from gravitational instability, right? It looks like it would be really hard to explain all of these detections with core accretion. So the main result that come out of this sort of survey is that these brown dwarfs and on really wide orbits that we were finding in the earlier surveys probably come from gravitational instability or top-down stellar mechanism, but it has to be inefficient. because we're very sensitive to what we expect to come out of this formation process, but we're not seeing that many things. So if gravitational fragmentation was very efficient, we should be seeing so many more brown dwarfs, and we're not. So we think that this is where they come from, but there has to be a somewhat inefficient process. And now on the right here, I'm plotting the detection limits that I showed you before for the VLT SHINE survey. So you can see that over time, we've actually improved what we can do on the observational side. So we're probing smaller masses, but mostly tighter separation. So we're really reaching within 10 AU down here, which we weren't really doing before with NACO. And in particular, we start having more planets as well. We have like 2 new detections within 10 AU that we didn't have before. And in parallel to this progress on the observational side, we also have new co-accretion models that now include more planet scattering and migration. And actually, with these newer populations, we start seeing an overlap between the expected outcome of the co-accretion population and some of these planets that we're seeing. So these new detections start being in the ambiguous part of the parameter space that could be due to both co-accretion and gravitational instability. So what we do then is that we try to fit this, all these observations, so our detections and our completeness of the survey, to both population, to an overlapping population of gravitational instability and co-accretion. And our results essentially point to the idea here that there are more we're starting to find more planets as we're reaching tighter separations. So the planet occurrence rate increases as we get into smaller orbits. And these seem to be better explained by a co-accretion origin. So we have smaller, closer-in planets better explained by co-accretion, and then wider, more massive brown dwarfs better explained by gravitational instability. There has to be inefficient, or we would see many more. Okay. So then another astrophysical question that we can try to answer with these occurrence rates is whether there might be a dependence on stellar mass in the type of planets that we can see or the frequency of planets that we might find. And for example, we know that small rocky planets are quite abundant around low mass M dwarfs. For giant planets, we need a lot more material to build a giant planet or a brown dwarf. So that means that you need a much bigger disk. Typically, we find those around more massive stars. So there are reasons to believe that it would be easier to form giant planets or brown dwarfs around more massive stars. So maybe there's a correlation there. And in particular, all of our favorite systems that we find early on happen to be around pretty massive stars, like more massive than the sun. But the question is whether this is a real thing, whether it's a fluke, whether it's just small number statistics, whether it's a bias in how we discovered these first systems. So we need to do some proper statistics to see whether there really is a correlation between stellar mass and planet occurrences and properties. And the GPI survey did exactly that. So the GPI sample was divided between stars more massive and less massive than 1.5 solar masses. And by constraining the occurrence rate of planets within this mass and separation range, they find a statistically significant difference between the occurrence of planets around lower mass stars and higher mass stars. So there seems to be more wide orbit giant exoplanets around more massive stars. And then these results actually, they're in very good agreement with what we know from the RV population that also finds a higher occurrence rate of planets around higher mass stars compared to the lower mass stars. And they point to this idea that, again, we were already seeing in the RV population, that planets around more massive stars might have a separation peak that is further out. So we know that for sun-like stars, the giant planet population has a separation peak around 3-5 AU. And that seems to extend out to maybe about 10 AU for the planets around the more massive stars. So we have different masses and separations for the planets around more massive stars that appear to be more frequent. The SHINE survey kind of reached similar conclusions, but by approaching the problem in a different way. So what was done in SHINE is that the sample was divided between massive BA stars, sun-like FJK dwarfs, and then lower mass M dwarfs. And in all cases, the underlying population that was observed was fitted by a binary component and a planetary component. And what we're seeing here is that there seems to be an inversion in the dominant formation channel as a function of host star mass. So what we're seeing is that we're constraining all sorts of substellar companions. So we're looking at things of like similar masses, like absolute companion masses. But we're finding that the sort of companions that we're seeing around the BA stars are better explained for most of them by a planetary origin, while the same masses that are seen around M dwarfs are better explained as coming from a binary channel. So it's kind of thinking about this in terms of mass ratio. We're looking at companions of roughly similar masses, so massive giant planets and low mass brown dwarfs, but around the small stars, they have a higher mass ratio, so they come from like a binary origin, while around the BA stars, there would be more giant planets forming in a disk. So this motivates the idea of doing specific surveys dedicated to the most massive stars, which seem to be harboring more massive planets that we might be able to detect with direct imaging. So that's exactly what some people did. So there's the BEAST survey, so the B star exoplanet abundance study conducted with Sphere DVLT. That found these two really interesting systems. So they're massive giant planets of 11 and 15 Jupiter masses on really, really wide orbits and around very massive stars. So these two detections confirm this tendency towards lower mass ratios and wider orbital separations for giant planets around massive stars. And they were actually detected around the very first and the seventh star that was observed in this study. So that initially pointed to the idea that they could be super frequent. People got very excited about this. Unfortunately, that was it. So the plot here on the right is showing the preliminary statistical analysis from this survey. So it's only for about half of the sample. It's not the full thing. And you can see that the occurrence rates that are constrained for the BEAST program, which are the red distribution, they're really, really broad. So at the moment, from the statistical analysis, there's no evidence for different occurrence rates between these massive stars, and the green ones are the results from the SHINE survey. But they're really broad distributions, so we kind of need to have larger sample sizes to try to see if maybe they separate or not. It doesn't mean that there's no correlation. It just means that with the data we have at the moment, we can't distinguish the two distributions. But there are other studies do point to the idea that more massive stars tend to have more wide orbit giant planets. Okay, just to go back 1 second. So you may have noticed that this system here, the inner star is actually a binary. Okay, and that's not the only system that we know in direct imaging. There are a few examples of the directly imaged system that we know that have been uncovered in binary systems. There's two main different classes of planets in binaries that we can have. So the first one on the left, with my little PowerPoint drawings, are showing what we call second binary or p-type systems. So this is when a planet is jointly orbiting two stars that are on a close orbital separation. And then on the right, we have what we call circumstellar or S-type systems. So this is when the planet is orbiting one star, and then far out, you have another star that is orbiting this star plus planet system. So we know examples of direct imaging detections around both, and that's despite exoplanet science being very biased against binaries. So historically, it's true for direct imaging, it's true for transit, it's true for RVs. We have been ignoring or avoiding as much as possible binaries because they make everything complicated and people don't like them, which is unfortunate because binaries are super cool. But despite these biases, we actually ended up with some of our few detections being in binaries. So maybe there's something there. So there's multiple reasons to try to study them. We want to know whether the presence of an outer companion helps or prevents the formation of planets. It could go either way, whether they help them survive or if they eject them from the system. Many things could happen. And one example of a motivation to look into this, I was part of a study a couple of years ago where people modeling gravitational instability in disks looked into whether the presence of an outer star companion, which is shown here, can actually impact positively or negatively what happens in your disk. And what I'm showing here is a disk that is stable if it doesn't have the outer companion. So this is a disk that never fragments by itself and never forms giant planets if the star is alone. But by adding an outer binary companion on a separation of a couple hundred astronomical units, that companion was able to push the disk over the threshold for gravitational fragmentation, and it allowed that disk to form little baby planets and brown dwarfs here. So it hasn't been confirmed, but it points to the idea that maybe the presence of outer binary companion can help the formation of giant planets. So maybe that's something that we should look at, especially with direct imaging. So these are the two main surveys that have been conducted to date to try to constrain occurrence rates of planets around these two types of circumbinary and circumstellar binary systems. The results at the moment show no evidence for any positive or negative impact of multiplicity on the occurrence of direct imaging planets. So we're finding compatible occurrence rates with all these other values I've been showing you so far. But it's still small number statistics. There's still some biases in all of this. So it's still something that is worth exploring. We know that stellar multiplicity has some impacts on some of the demographics of closer in planets. So there's definitely more to be done on this side as well. Okay, so we've explored extensively this part of the parameter space. We now know that occurrence rates are not very high. Of course, there's still many things to improve. We can keep staring at hundreds and hundreds of stars and maybe find a few more planets and improve statistics. But if we want to make more progress now, we really need to find more planets. And that brings me to the second type of surveys that we can do with direct imaging, which is these targeted searches, where the goal is really to try to find more planets so that we can better understand this population of giant planets in the parameter space we're currently exploring, even if it means that we're biasing ourselves and can't really do statistics out of these. So Sarah gave a really beautiful introduction to this morning, but basically the idea is to use signatures of hidden companions around a star as a pre-selection for the stars that we try to image. So this can be done in two things. So we know that when we have a companion around the star wobbles around the center of mass of the system. And that can lead to two trends, often a combination of both, but the motion of the star in the line of sight is going to be seen through some radial velocity trend. And if it's in the plane of the sky, we're going to see this through an astrometric wobble. So people have been doing this. They've been looking at stars with really long-term radial velocity trends, which is an indication that there's a companion far out. If it's far out and massive enough, maybe we have a chance to image it. And a couple of mostly brown dwarf detections have been discovered this way. And then in parallel to this, mostly in the last couple of years, there's been this growing attention given to these proper motion anomalies. So multiple teams have started around the same time trying to use, for example, Gaia proper motion anomalies, Gaia accelerations, to try to predict the sort of masses and separations that could be compatible with the Gaia trends, and try to decide if it's worth going after this star with direct imaging. And that has led to quite a few detections. And actually, it's been a pretty significant boost in direct imaging detection. So I'm showing here a couple of examples. So I led a little program with Sphere where we selected only 25 stars that had these Gaia accelerations. And we found 4 new brown dwarfs out of 25 stars. Okay, with blind surveys, we've had to image hundreds of stars to maybe have one detection. So this is super efficient at detecting new directly imaged companions. You've probably heard about these other systems here. We've talked about AFLab-B a couple of times. And actually, I want to highlight that we've been boosting the number of detections so far, but a lot of these actually came from the same few teams. So most of the detections we've made have been simultaneously found by multiple of the teams doing this, which is always a good scientific validation, of course. But hopefully with the next Gaia data releases, we'll have more of these stars with stellar accelerations, and hopefully these numbers are gonna keep going up. And I wanted to highlight, you may have seen this super cool paper published by Elizabeth Matthews that came out yesterday. So this team managed to directly image a very, very cold planet of only 275 Kelvin with James Webb in the mid-infrared. And this is a star that was known to have something hidden around it from long-term radial velocity data and a bit of an astrometric acceleration as well. So this system was selected exactly through these methods, and the companion was found. And we would never have been able to find something this cool from the ground in the infrared. We really needed to go to these wavelengths with James Webb, but this is really opening a whole new part of the parameter space, which is super exciting. So as Sarah said this morning, we can use relative astrometry, but also combine it with absolute astrometry and radial velocities to constrain orbits. And this is really cool with all these all these new stars that we're finding with Gaia accelerations, because the Gaia hyparcoside data basically gives us a 25-year baseline on the information of the orbit. Okay, when we started discovering direct imaging systems, we had to wait years, if not decades, before we started seeing a bit of orbital motion for the HI 799 planets. So we've had to wait a really long time before being able to actually get model-independent dynamical masses for these systems. With all these new systems that we're finding through these methods, we can already try to constrain the orbit almost as soon as you have the first direct detection. And that's really valuable because it's providing us a lot of model-independent masses, which is really important if we want to try to validate and test the evolutionary theoretical models that a lot of our results are based on. So this is showing you some of the directly imaged companions for which we now have dynamical masses. And you can see that they're mostly in the brown dwarf range, like we still don't have that many for the lowest mass planets, but at least we're starting to get to a point where we can sort of better validate the theoretical models in this part of the parameter space. And then the second cool thing with having all of these dynamical masses is that we can do more than just constraining occurrence rates now. It means that in terms of demographics, I can actually start looking at the distribution of masses, the distribution of eccentricities, and all of that, which we know is going to be a tracer of formation. And so Brendan Bowler actually did this. So here what we're showing is the eccentricities of directly imaged planets and brown dwarfs for which we have some orbital constraints. And what we're finding in this is that there seems to be two distinct substellar populations. So confirming what we were thinking about this idea that there are multiple formation channels for this image, that for this population we're seeing. And this is validating this idea by essentially highlighting that lower mass giant planets or the lowest mass ratio systems have much lower eccentricities than the highest mass and more wide orbit brown dwarfs. So really confirming this idea that we are seeing two distinct subpopulations. And just to come back to this plot, I also wanted to highlight the importance of constraining these models. And in particular, a lot of these models and what we assume at the moment have this, what we call a hot start. So assuming that the planets are born with a lot of entropy, they're born really hot. But there's also the possibility that especially the lowest mass objects down here could have a cold start, so with a much lower initial entropy. And that's a bit dangerous for us if it's true, because it means that we could be hugely overestimating how well we're constraining occurrence rates. I'm going to say this in a better way. Basically, what this is showing is that if we assume these hot start models, we assume that planets of these masses that are predicted from our co-accretion model have pretty high temperatures and high luminosities that we are sensitive to. So if we compare our co-accretion models that predicts a few planets with these masses, we use these models to say, okay, they should have these luminosities. That falls within the parameter space that I'm detecting in my survey. So I can place a pretty good, depending on how you define things, upper limit on my fraction, on my occurrence rate when I don't see anything, because it means I should be sensitive to where these planets fall. So if I don't see anything, I can place a strong upper limit on my occurrence rate. If, however, these same masses of planets have a cold start, that means that my model is not predicting any planet in the part of the parameter space that I am sensitive to. So I'm not seeing anything, but I'm also not expecting anything there. And where the planets are, I have very little sensitivity. So that means that for the same survey, depending on what you assume is the initial entropy of your planets, you go from placing an upper limit on your binary fraction of about 20%, this is from the Leach survey, to placing an upper limit of only 90%, because you have very little sensitivity to where you expect your planets to be. So we do think that, at least from the model independent masses we've been placing for the brown dwarfs, we're confirming that the models we have at the moment with this hot start are probably correct for brown dwarfs, but we don't have that many points for the lowest mass planets, which are the ones that could have a cold start. So it's really important to get more dynamical masses at these lowest masses and confirm that they do have a warmer or harder start and not this cold start, which would mean that we're not really constraining things as well as we thought we were so far. So yeah, the bottom line with this is that actually, if these planets do have a cold start, they could be a lot more common than we think. It's just that we haven't had the sensitivity to actually see them so far. And finally, I wanted to end on a slightly more optimistic note, which is that with James Webb, as I've just shown with the detection of EBS in the AB, we are actually finally probing a new part of the parameter space of really cold, low-mass planets that have been inaccessible so far. So in particular, this is a plot from one of Aaron Carter's James Webb program, is comparing the detection limits from the VLT Shine survey to what we can do with James Webb for the Better Pick moving group. And you can see that with Webb, we're finally able to probe sub-Jupiter masses for the very first time. And that really motivates the need for new blind surveys. So you may have heard before, I know that during my PhD, I heard so many times that James Webb is a characterization mission. I think we should push for blind surveys, and I'm really glad that some people did. So Beth Biller and Erwin Carter got a bunch of blind programs to try to measure occurrence rates in this new part of the parameter space. And this is really important. So we know in this part of the parameter space, we've observed hundreds of stars, we have a good idea of what's going on. So now we can do things in a more biased way just to get more detections. But whenever we're going to be opening the parameter space to a new region, I think it's important to go back to blind surveys so that we can do proper statistics and actually infer occurrence rates and measure demographics in new parts of the parameter space. So accessing these masses for the first time with James Webb, and then in a few years we'll have the ELT, which are going to help us probe much tighter orbital separations. Okay, so time for my very chaotic summary. The main thing we know is that wide orbit giant planets and brown dwarfs are not very common in the part of the parameter space we've been looking at so far. We know that, or we believe that brown dwarfs, so the more massive and wider orbit companions we're finding, probably form through some disk instability scenario or a stellar binary channel, but it has to be rather inefficient for these masses. Otherwise, we should be seeing a lot more of these objects. And as we started reaching closer in orbits and smaller separations, we're finding that there's a higher occurrence rate of giant planets on tighter orbits, which points to the idea that these probably form from core accretion and extend the outer tail of the RV population. As we now have more information about orbits, we're starting to see two distinct substellar populations, which again point to the idea that the higher mass things probably form through some top-down mechanisms, and the lower mass things again extend the RV population from core accretion. There seems to be a preference for giant planets to be around higher mass stars, possibly with lower mass ratios and wider orbital separations allowed. The effect of stellar multiplicity is not really understood at the moment. And finally, there's a lot more things that I didn't have time to mention or that are still not very well explored at the moment, like the effect of stellar environment, the host star metallicity, a correlation between the existence of planets and the presence of debris disks, what happens with dynamical evolution, if we have initial entropies right. So a lot more things to explore. And I just want to finish by highlighting that, again, I think it's really important to keep doing as a field this combination of blind surveys whenever we are able to look at new regions of the parameter space. So that can be with new generation telescopes. It can also be with improvements on the side of how we look at the data. So whenever we have better processing techniques, we can go back to archival material, go deeper in mass, closer in separation, and reanalyze all of this. But then for things where we now have a lot of observations, we can do this in a more biased way and just try to get more detections and a much larger sample of companions so that we can better understand the overall population that is there. Thank you very much, and I'll take questions.
Perfect timing. Yeah, there is a question by Elle, I think, on the back. Do you mind? Yeah, I've learned so much. Thank you so much. Great summary. Good timing to make it as well.
Hi, Clem. Thanks so much for the talk. I have a question for you, which was asked to me 2 weeks ago and I couldn't answer it. So I was just going to throw it at you. And it has to do with the age, mass, luminosity, degeneracy, and the fact that planets don't always form exactly at the time that their stars formed, right? They might be delayed in some way. And so I was wondering how much that would affect uncertainties when you're trying to fit all of those things together.
Okay, so correct me if I'm wrong, the question is about how, if planets are formed later than what we think the age of the star is, how that affects things.
Yep.
It's definitely going to change a bit what we think our completeness is. So that's going to be the main. Okay, so when we try to measure occurrence rates, we don't have that many detections. So the main thing that we rely on is trying to estimate what we could have detected or what we may have missed. And if planets are not forming at the age that we adopt from models to derive these, our completeness changes quite a bit. And that's dangerous for the exact same reason as the initial entropy thing, is that if you get your luminosity or age wrong, then the part of the parameter space that you're looking at could be very different. So it would be, I don't think it affects the detections themselves, and we're finding dynamical masses that are roughly in agreement with the luminosity for a lot of these. But if there is a big difference, I think it could change a lot the occurrence rates that we're constraining. So I would be scared of that.
Yeah. Thanks.
Yeah, there is a question. I'll bring you and got you after. Thank you.
Hi, I'm Elena from Lighting Observatory. Thank you for the nice presentation. So I think you didn't have a lot of time to talk about it, but I was wondering how you are accounting for possible migration of these planets and brown dwarfs in this scenario where you expect a certain number, a certain occurrence, but then you actually don't find anything, but maybe they just moved or something. So I was just wondering about that.
Yeah, that's a really good question. So I'm not doing this directly. I rely on other people doing this. So mostly what we do is to compare observations to population synthetic models that look like these. And in particular, I highlighted the progress we've made on like the modeling of the core accretion things. The main thing that changed here is integrating dynamical evolution and migration and scattering, which is how we're finally getting low mass planets a bit further out. So without this, we can't really attribute any of the direct imaging detections to core accretion. So that's kind of like the main link that we have, is that by saying if we take models that include outer scattering, then some of these planets could be due to core accretion. We're still looking at mostly young stars, so things like dynamical ejection, I think, would take longer timescales, so it's not too much of a problem here. It will become a really interesting thing with the ELT when direct imaging starts probing tighter orbital separations of the RV population, because then the RV population tells us stuff about older systems. With direct imaging, we're still going to be looking at mostly young stars. So comparing these populations is probably the best way to start looking into the effect of dynamical evolution, because we'll have information about the same part of the parameter space at different ages, which we don't really have at the moment.
Thank you.
We had first a question here and then go to check the time.
Hi, we're Nest Talk, and I'm Xinyan from Tsinghua University. I'm very interested in these two distinct substellar populations, and I have two related questions. Like maybe you can back up to the slides. Yeah, this one.
Yeah.
So I'm curious about how you divided the two groups, like the blue groups and the orange groups. So I'm curious about like how you divide these two groups. Like, is the low mass ratios and high mass ratios, they are by definition reside in the exact mass range, or you just cut this artificially? And second, I'm curious about those points with eccentricity exactly to be 1, and are these real data?
Oh, at the top, yeah.
Yeah, from real observations, why their eccentricities are like 1.
So this is not my work. So this is Brendan Bowler's work. So I'm going to refer you to the paper for actual details in case I don't remember things correctly. I think the mascot is put on the upper panel at 13 Jupiter masses. So just typically taking what we adopt as the limit between brown dwarfs and giant planets. We do think if there are these two overlapping populations, they shouldn't be a strict mascot. They are going to be like an upper tail of one formation overlapping with the lower tail of the other population. But this is kind of like a preliminary way to start looking at whether there is something there. Again, we'll never be able to tell for sure this planet formed this way. It's very unlikely we'll be able to do this. The idea is more to look at things overall and start to see if you see signs of two distinct populations as opposed to one. So I'm not arguing that this is the best way to do things, but it seems to be a good way to highlight that there's something interesting in there that we should push for. I don't remember how that limit was placed for the mass ratio. It looks visually like he just took a limit at 0.01, but I'm going to have to check the paper to confirm whether there was a stellar mass dependence on this as well. And for the high eccentricities up there, I'm not entirely sure how physical they are. Sarah highlighted this morning that if you have an incomplete orbit, you can have some high degeneracies between some of the orbital parameters. So it could just be an effect of that for some of these. Yeah.
So maybe it's just the upper limit of the eccentricity or something.
What? Sorry.
Upper limit of the eccentricity or something.
I don't know.
Thank you.
Hi. Thanks for a really interesting talk.
Where are you?
Hello.
Who's speaking? I don't know where I'm looking. Oh, sorry.
I'm really interested in the connection between planets and debris disks. Is there any studies looking at the connection between like the prevalence or the properties of the debris disks and planets?
Yeah, I didn't have time to cover this. There have been some studies looking into this. My understanding is that was also a bit inconclusive. So there was a paper in 2017 that did find a correlation between the presence of debris disk and the occurrence rates of planets. More recent radial velocity results are not finding this to be true. So I think, yeah, it's still an open question as far as I understand it, but there doesn't seem to be that much of a correlation, at least within the error bars and data that we have at the moment.
Unfortunately, we'll have to cut the questions here. So